All right, we're getting started on the third week of this x64 practice on Project Euler. And last time I noticed the next few problems, well, we skipped some of them, but several of these problems, so problem 8, problem 11, and problem number 13. Yeah, these all involve needing to parse data in order to actually you get to the part where you solve the problem. So before we go into the x64 programming part, which we'll try to get to before too long, but we're going to try to just throw in a really quick solution so that we can parse this stuff. Basically, what the parts we're going to need, maybe I'll draw this out on Milton, but I'm going to explain it first without that so I can look at the sample data. I need to put this into a text file. And then I could also put that right into a string literal, I suppose, but I need something that can take text that looks like this and turn it into a one-dimensional array of integers for this problem, but each of these being one of the integers, right? Each of these is a digit. For this problem here, we want to treat it as hex, so we're going to say like each two digits. Maybe it's not actually hex, it's it looks like it's still in decimal. It's just up to 100. The numbers go up to from 0 to 99, right? that makes some sense. But anyways, so we want to be able to parse. Maybe I want to be able to parse as base 10 or base 16. I want to be able to say how many characters per number there are, and I want to be able to say whether or not the lines should be treated as splitting a two-dimensional thing or if it should be one-dimensional. I don't necessarily need to be able to say all of that, but I need to be able to get the effect of saying all of that. So if there are some things that I can get both ways without having to do extra work, like I think I could do two-dimensional and one-dimensional at the same time for everything. So I want to just get a parser ready that can do all that. And then we can skip to actually solving these problems without having to write a separate parser for each one. But if we don't write the parser at all, we'll just be skipping these problems, which they're not like, they're like a different category of problem that might reveal some things about x64, and we won't know until we try. So for the purposes of practicing, I want to dig in and try it. Hey, Dan. BYP64 is asking a question that I want to answer. So for the 1,000-digit string, I think that's this one, yeah. So I could take these, and I could take each one of these and subtract 0. But there's still it still has new lines in it. It still has, I still need to put it into a data structure. So if I wanted all of my arrays to be a byte in size, that would work. So maybe I could actually think about it that way. Could I do all of this in a single byte? Where was that? Progress. So problem 11 goes up to 99. So those fit in a byte as well. So yeah, each of these could be done with a byte. I think this one also had, yeah. This could work as a byte. There was another one a little while later. This one also looks like it would work as a byte. So yeah, that's one good point is we'll be creating an array of bytes because none of these look like they need to be parsed into integers larger than that. Now, do I want to do it in ASM? I suppose I could. I mean, what I would be practicing then is processing text into processing an array of bytes into another array of bytes. I mean, we're already going to be doing array processing as a part of the actual problem. So I think the thing that's most important to me is I don't want to spend for all of these separate problems. I'm not really interested in fiddling with the ASM because it's already kind of fiddly to write a parser anyways, right? Writing a parser is a thing which is on its own kind of error prone. And then doing that in assembly by hand won't necessarily be that instructive. That's something where I think a high level or a more high level thing adds a lot more value than in some of the math stuff where it's that we've done so far. I don't know. Maybe it's just an excuse. We could try it, but I want to avoid having to write 3 parsers. So let me think if that would be. So like, let me like sketch out the design for the parser, and then I can decide it. Like, I'm gonna sketch it out in a language agnostic way, just thinking about the data transforms that I want to have happen. And then if it looks like something we could just do in assembly, maybe I will do that. But I want to like do a little bit of planning here on what the parser part looks like before I make a decision on the language. So this is problems 8, 11, and 13. Okay. Let's sketch out some ideas. Parser for problems with input data like numbers 8, 11, and 13. Okay. So I want to be able to handle a couple of different cases here. There's single digit versus 2 digits. So this is like values in the range of 0 to 9. And this is values in the range of 0 to 99. I guess we only need decimal because we haven't seen any real hex. So let's just say it's always decimal, and it's either 2-dimensional or it's 1-dimensional. So now the goal is, can we come up with any tricks that will let this all work as one code path? So I think the first thing that comes to mind is that I think this one is pretty easy to deal with if we just, the block of memory can be the same in both cases, right? You just parse it as a block of memory as if it's going to be 1-dimensional in the actual memory, and then you emit all the data for doing it both ways. So so let me think. That would look a little different in that problem, like this one, or is it this one? Yeah, this one here, it's not a 2D array. It's not like a square array, right? So it's like, you'd have to do something different with the dimensions here. But you could still parse it as a 1-dimensional array, and then, okay. All right, I have an idea. Okay, I know how to, I think I know what we want to do. So what we're gonna want to do is we're going to want to have, we could handle both of these. Code path. And here's how we can do it. So like thing number 1, always output 1-dimensional data, right? Array, whatever. And then 2, output the number of lines. Oops, let me make that a little cleaner. The number of lines. And so, which problem was it that we were looking at there? 18? Yeah. So for problem 18, so these are like, or 18. So for a problem like that where it's not a square, we would want to treat the number of lines in a different way. So the idea is like, in 2-dimensional case, well, let's first of all start with, in the one-dimensional case, we ignore the lines. In a two-dimensional case, two-dimensional rectangular case, we do total count divided by line count to get the like y stride, right? And then in the case of like the triangle one, in 2D triangular case, we figure something else out. But that thing we want to figure out, I don't want to do the details right now, but I think it's pretty clear, like at a glance, that that'll follow from the number of lines as well. So someone in chat, Mophilia, asks, hi, do you have a repo for your solutions in assembly? I do. I haven't made it public yet, but I will do that when I can. Probably at the end of the month, or maybe a while after that. But I'll announce it on my Twitter whenever it's finally available. If you're not following me there, you can follow there to see it. Or I can send you the repo that it'll go up to eventually. I'll do that real quick. So here is the repo. If you are following that repo, it will have the solutions eventually. Okay, now I want to think about the other part of the problem. How can we handle the single digit or the two digit cases? So it seems to me like that will be something we have to like parameterize on dynamically, right? Because we're not going to produce the data. Like in this one, we're basically saying find some way to produce one kind of data that works both ways. There's just not going to be any way we could do that here. If I like say always treat it as a single digit, then I'm going to have to do a second pass to convert it into a two-digit case afterwards, and that just doesn't seem as good, right? The second pass to like completely do a conversion of it from one size, it's like doing a in-place conversion of a buffer is one thing, but when it's going to also change the size of the buffer and it's going to involve like multiplying by 10 and then adding that to the next thing or whatever, like it's just kind of goofy, right? So I think we'll try to just have a number of digits be a parameter, like a runtime parameter to this thing. All right, so that's kind of the sketch of what I want to do. I'm still going to use a little bit of help from the C code just to get it started so that it doesn't have to like actually grab the raw string from assembly as well. So what I'll do is I'll start by grabbing this as our example. I can clear out the code from the last problem. Don't need you. So here we go. We're going to go. Let's see. This is Euler problem number 8. Euler 8 text equal. Let's do that. All right. Let me see if I can turn that into a macro. Quote slash end quote. Boom, 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 boom. Okay. So there's our text. And then we're going to try to write this in assembly. I guess that'll be the right thing to do. So that'll be our text for array. Let's get a couple of these. So if we go ahead a few, this is not the fast way to move around here. 11. Let's try this one as well. So these two are totally different. One of them is one-dimensional single digit. The other one is two-dimensional multiple digits. And I'll grab one more. I mean, another thing I could do is just say screw dealing with like the spaces and stuff and fix it by using a for-coder macro. Like I could just do more processing on the text here using my immediately available tools, which, I mean, I could be okay with that. I'm not setting out to write like a super elegant parser here, but I don't know, maybe it makes sense to practice dealing with strings for a bit in assembly. So let's go down that road, see what happens. Don't want to skip out on a chance to learn what might be going on in there that's unique. So, all right. Yep, those will be our test samples. And wow, that last one's big, huh? And then all we want to do is parse them into an int32 array. So let me set up first of all the C side. This is going to be an array of U8s. Byte data from Euler text. We need arena. We need text. Well, let's use our text. Actually, why don't we do that in all of these as well? Actually, no, there's a good reason not to do that yet. Okay. So in comes the text. Out's going to come the array. We do not have array U8s yet, so let's grab that real quick. Very good. And then we want to allocate that. Text.size, so we need to know the number of digits. Number of digits. Result.count. We'll get then the byte data from Euler text asm. For this, we will pass it the text.str, text.size, and then actually, let's practice passing in a struct, and then the number of digits, and then the output vector or array memory, right? So then what'll come back is a count here, and then we're going to do push or arena pop amount, and the amount that I want to pop is the amount that I took minus the amount that I actually used. So this will over allocate a little bit because it'll allocate for new lines and spaces, and it'll treat double digit to single digit, so it could be, multiple times bigger than it needs to be. We'll run the parse, and then what comes back out will be the actual number of bytes that it used in the output stream. But we need more output than that, right? So we need Euler. We didn't end up coming up with a namespace for any of this either, which we should have done. Well, who cares? Euler text parse, and we need to know the byte count and the line count. Let's do it like that. Or array count maybe, or yeah, element count. and the line count. All right, so for this to work, we're going to need to get back more than just that. Let's change this up. This is going to be memory result.count. We can put this here, so this will be parse.element count, element count, Euler text parse, parse byte data from Euler asm. We're going to pass in a struct of text, the number of digits, and the memory. And then we want to return the parse data that we need to move forward. That gives us a line count. And so then the other thing I don't have yet is I don't have built in a way to return. Let me think. I'm only returning the array right now, and that's not right either. So this is where it gets a little weird because we're trying to cross the boundary between assembly and non-assembly, so that we don't have to deal with the arena in the assembly, just because I don't want to have to call into the C++ functions from assembly, let alone deal with the fact that it's actually like wrapped in macro. Like, we have convenience stuff here I want to rely on, and now like if this is returning the array, it should actually also be returning the line count anyways. So do we have like two of these things? Right, so one thing is like we keep this very tight and we say like this returns just what it creates, and then this here has like v count line count, right? We have something like this. We have something like this going on, and then we have to like give these two separate names. So this is like the Euler text parse asm, and this is the Euler text parse, and the only difference is that this one is returning the whole thing, whereas this one is not. If I were writing this all in C, then I would just not have this, and I would build just this thing, because this one code path would do the set up the struct and fill it. But we're trying to get both of these back. So another thing we could do is use just this one, and then have like this be the result, and then have this here return that result, and just set the memory separately. That might be a fine way to do it for now. Yeah, I think I'm happy with that. That keeps everything relatively small. The only quirk is that the V element doesn't get filled until marina popum, or until after the asm function. Yeah, okay. Gotta write that. So this will be a text parse. Let's rename that. So instead of calling it an Euler text parse, this is like, I guess we didn't need the array U8. We needed like Euler data, and we have like line count, right? And this is Euler data here. So we need that. This doesn't need to exist. Okay, so now we just need to write this assembly function. Let's work on that part. Euler data byte. Let's just rename this Euler data from text. Euler data from text asm. That's going to take a string 8, num digits, and the output memory, right? Something like that. Alrighty, so let's figure out what the parameters are here. So RCX is going to be for the return, so that's going to be our Euler data, return pointer, right? Return pointer. And so at the very end, we're going to want to make sure that REX gets set to that return pointer. RDX, well, first of all, where is text going to go? So text is too big to go in a register. So I think that means we'll have to figure out where text goes, and that this will be num digits. And then R8 will be memory pointer. And then somewhere on the stack, we have the text. Now there was another case where I did something where I had to read something off the stack. Yeah, here we had enough parameters. But the fifth one was on the stack, and it was like this big amount here, which actually ended up growing by more because it's like 1, 2, 3, 4, 5, 6 additional pushes got thrown in there. So yeah, that's why this is 30 more than this now, because each of these is worth 8. So 6 of them becomes hexadecimal 30. So maybe mine will be at that amount as well. Let's go and verify that first. So the way we'll be able to tell if that's true is that we can call our function here. If we can shrink it up now. Let's do it like that. We can call this function here. And see if it looks like the right text. So I want Euler 8 text to get started. I guess I'll grab all these real quick. Text 0 Euler 8, yeah. That can work. There we go. So if I go to our debugger and I step into that that function call there, I want to see that all of these make sense for the parameters they're supposed to be. So RCX should be a pointer. RDX should be the, okay, RDX is not the number of digits. R8, that looks like the number of digits. And what's at RSP plus OX? Oh, sorry, I can't do it that way here. What's at RSP plus OX28? This thing, which also looks totally different. So why does it look like that? What is the memory pointer, by the way? So the memory pointer is hexadecimal 25 dB, etc. That, when I look, why does it, I don't know, it's weird. When I look here, that matches what's at the return pointer there. That's weird. Why would my return pointer be the thing at RSP plus OX28? What are these? This is so not what I expected. Why is number of digits in R8? Let's take a look. So we have 3 of these. The third parameter is getting the num digits. What is RCX pointing at? I don't even know. I don't know how to read this. I don't know if that must be the address. Yeah, that must be the value of RCX. So RCX is pointing at something on the stack. I assume, okay. Let me look at each of these. RDX is pointing at something on the stack. Here's the current position of the stack pointer. If you go back 8, so if you make this 8 larger, then you have 600 is right before the call. 20 more before that is whatever this is, which I think we determined is actually matching the output address. Okay, so memory. Okay, BYP is trying to help out. Let me read what you're saying in a minute. I started to get on the right track here. So memory is a pointer, and that's the third parameter, and that one's on my stack. Okay, what's at R9? Maybe I should peek at that. Okay, so it's actually at R9 as well. Right? So memory, wait. Yeah, so memory, the memory pointer is in R9. Okay, that I know for sure. Here's my memory pointer. Now, why are these other ones all so wrong? So I thought the first one would be the return pointer. The second one would have to be on the stack because it's too big. This one would go into the next register, and this one would go into the next register. Apparently, so what you're telling me, BYP, is that RDX is not on the stack. Or rather, it's on the stack, but it's also going into my register at RDX. Is that what you're saying? I see. Okay, so if something's too big, that doesn't mean it doesn't get a register. That just means that it's a register that points to something on the stack. And then if there are things that overflow the registers completely, those also go on the stack, but that's a different sense of it being on the stack. I see. So when something's big, it just gets passed as a pointer. So this is just pointer to text. This is my return pointer, so this is a pointer to Euler data. And that makes this num digits. So my return pointer is this guy. First parameter, second parameter, third parameter. Okay. There we go. And then I don't actually need to go digging into the stack pointer in order to find my next parameter. So that's good. Okay, so we got the parameters. I think all of that made sense. So the next thing is, how do we write the parser? So it's going to be in... All right, we know we need a loop that can like visit. Okay, got it. So we want to start by setting RAX to be, let's say, putter equals memory, right? So that's going to be our pointer, RAX. Wait, why don't we use R9? Is there any reason? Is there any reason for R9 not to be the putter? I don't think so. So I do need... Oh, this is the output. Okay, I see. So if text... Okay, I need to set putter equals text.stir. So we're going to move into RAX. Whatever you find when you read off of RDX, because RDX will be a pointer to a string 8, and the first parameter of the string 8 should be its pointer. So this will set RAX to our pointer. And then we're going to say we don't need RAX or RDX anymore. So we're going to have one pass last equal putter plus text.size. So the way we'll do that is we want to first move into RDX the thing we find at RDX plus 8. So we're going to read 8 past the pointer. RDX pointer points at a text struct. 8 bytes after the pointer to the beginning of the text struct, we find the count of the size of that text struct. We put that count into RDX. Now we have the putter here, and we're going to do set RDX to be equal to the memory address you get when you have RAX plus RDX, right? So here's the offset we want, and then here's the pointer we want. So we put them together, and we get the one pass last pointer. So now we can write a loop. And the loop is going to go like this. If putter is greater than or equal to the one pass last pointer, go to done. So compare putter RDX, jump if above or equal. So that's doing it unsigned, which is what we should be doing for pointers. Jump if above or equal to done. And I'll put a done 0 label over here. So there's our exit condition. Now let's do our increment. And our increment looks like this. Putter plus equals 1. Go to loop 0. We're going to increment the putter and jump to loop 0. Okay, so there we have a loop that is going to visit every character in the input text. Now, let's see. Let me make a to-do list of features we need to add. So one is count the new lines. Another is how do I want to put this? Emit numbers, right? Okay. So let's start by trying to count the new lines. Well, first of all, let's pick a spot where we can read in. RCX is the return pointer. I'm gonna want somewhere where I can, at the end, I'm gonna want to set into RAX the value at RSP, and then we'll have to add 8 to RSP. Up here, we'll subtract 8 from RSP, and we'll set okay, so we're going to set this to this. And then I have RCX free. So what I want to do is I don't need technically I could do that. Euler data. So at the very end here, I'm going to want to set the v count and line count. V will be this memory pointer. So let me fill that in now. So this is result dot v equals memory. So I'm going to move into RCX plus 16, the memory pointer, R9. Oh wait, V is not plus 16, that's just at the beginning of the struct. Okay, so result.v is this guy, so RCX plus 0 gets the R9 memory pointer. Okay. All right, so let's take a look now at this part, counting the new lines. So I'm going to need to read. The reason I was doing all that is so that I could free up the RCX register. So now I'm going to say we can use RCX. Let me just see how I'm allocating these. So RDX is our one pass last, and it's taken. RAX is the pointer that we're using for reading. So RCX is going to be where we actually store the value from the pointer. What is num digits? Okay, num digits, we'll just need that all the time when we're doing the emit numbers part. Okay, so let's say like C equals dereference the pointer. So we're going to move into RCX, the value from RAX. But we don't want the whole thing, we just want like a single byte. Oh man, is it like that? Cool. So we've got the C character thing. Now let's do some tests on it. If C is equal to new line, then go to inc line counter. So we want to compare RCX. Now, does MASM have like character literals? Not really wide, that's not what I need. Numbers, pi, data in either single or double quotation marks can represent character strings. The following are all valid strings, no embedded quotes. So I can write ASM that looks like, is this true? I can do like this. Does it have like, programmers aren't able to insert new lines of code very easily. Symbolic news. No, that's not what I want. Okay, where's line 8? Looks like you don't use, okay. So 0AH, is that the one you need? Yeah, we'll do that. Okay, so if RCX is equal to that, so jump if equal to inc line counter. Inc line counter. We haven't chosen a designated line counter yet, but I suppose we'll make R10 the designated line counter. So inc R10, and that can go right into this and keep going. So we're going to start with R10 has to get cleared to 0. XOR R10. I'm pretty sure R10 is one of the volatile ones. I don't have to save that on the stack and restore it later if I use it. Okay. So I don't need this anymore. What am I looking at this for? The next thing I need to do is emit numbers. So for that part, what we want to do is more tests here. We basically want to say if C is less than, or if 0 is less than or equal to C, and C is less than or equal to, this is an interesting thing. We haven't done like an AND concept before. Then we want to do go to, I guess here we'll probably want jump loop 0 next, loop 0 next, go to process digit, and so there'll be like a jump here of some kind, don't know what, that goes to process digit, and then if that doesn't happen, there'll be a fixed jump, just write it like this. There'll be a fixed jump that goes to loop 0 next. So it's like, hey, this wasn't any of the characters we care about, so it's like a space or a, carriage return or some other garbage. So we just skip this character. We'll make this parser kind of sloppy like that. That way it's easy to get it working and we don't need to report errors or anything like that. Okay, so now we just want to figure out how do we want to implement this, because we can easily do one comparison, but how do we do two comparisons? One could be that we invert this, right? If I could make it so that it's OR, then I could write, like, you can't write an, how do I want to put this? If I write an AND as two jumps, right, it would be invalid if I were to write this. If C is, if that, then if that, right, this would be an invalid way to write the AND, right? So here's the thing I actually want. If I wrote this, I would get the wrong result because I would just jump right away anytime, this was true. And if that was false, I might jump when this is true, but I need them both to be true before I jump. But I could invert it and say that I am gonna put a not here. So if this is not true, then go to loop 0 next. And otherwise, we just immediately process the digit, right? So it's like process digit's the automatic thing. So that could be done. The only thing then is we'd have to, well, yeah, we just have to like apply a little bit of, what is that called? DeMorgans Law logic there. So we end up with something like this. If 0 is greater than C, or if C is greater than the 9th digit, go to loop 0 next. I saw there was something in the chat. Let me peek at it. So tip from the chat says biased compare. That's a good idea. So what that means is instead of, so what I originally had, let me write it again. What I originally had was good. Go to, let me back up. Okay, so the question was, how are we going to do this? So their suggestion was bias compare. So if we were treating C as unsigned, what we could do is say, well, this will be true if and only if it's also true that we can pass this test, right? So if I just modify both of these by the same amount on each side, and I'm saying, look, anything outside of this range was invalid anyway. So like, yes, this is testing something different now, but altogether what we're doing is we're saying the set of things that are inside this new range are the same as the one we had before. So first of all, this becomes a 0. And comparison to 0 like this with an unsigned value will just always be true. Like once we do C minus this, yes, some things will be less than the 0 here, the 0 character, but when we do the subtract on the 0 character, those things become very large positive things. They're still outside of the range, right? So that just becomes, that disappears. And all that's left to do is to test this. So this here also just goes to that. And so all we have to do is modify C once. And we're going to want C modified anyway. So that's what we'll do. Here's what we'll do. We're going to say C equals C minus 0. We can call this like C, we'll call it like D for digit instead of C for character. How about that? And then we just say RCX, which is containing this thing, is going to get modified. So subtract from RCX. Now we want to subtract that. I don't know if it'll let me do this. But that's what I want to do. Okay, I think it's going to let me do that. So now we can say, okay, forget about this. Is D less than or equal to 9? If D is anything greater than 9, then we didn't care about it, right? So here we caught the case where we were looking at new lines. Then we're going to subtract a 0 from C. And then by 0, I mean it's the 0 ASCII, not the 0 byte or 0 value integer, right? So this now becomes a fairly easy comparison. Compare RCX to 9. And we want to jump if that is below or equal to the process digit. Otherwise, we'll do loop 0 next. Yeah, okay. So now when we reach here, RCX contains D, the digit, and all we have to do is process it. So let's first pretend that num digits is always 1 to make this easy. I guess the only cases are num digits equals 1 or 2 because we're emitting bytes. So if we emit something larger than a byte, then we could go up to, you know, like 3 or 4 or 5 digits. 6, 7, depending on how much bigger than a byte we go, we can get more and more digits. But for a single byte, we can only get up to, we could technically do 3 digits, but you wouldn't be able to do all possible 3 digits. You could only do some. So you'd have to do a lot of error checking or like just accept the rollover. But for 2 digits, we can just fit it in a byte without even having to think about it. So that's why I kind of think like 2 digits is the only other case we actually care about. Maybe we should just write those as 2 separate loops, now that I'm thinking about it. If there's only going to be 2 cases, I'm not sure that it makes a lot of sense. Let's try that. So this is going to change a few things, but I think it's worth it. We get a free register. We'll have to write this twice. But if that's going to be wrapped like that. Anyways, then yeah, we get a free register there. What is this? Data from text. Writing two special cases is a very different thing from writing like even just 3 or more. And so eliminating a parameter in order to make the code a little easier to write, it seems like a good move. So if we're processing a digit and we're doing the single digit loop, which is what we're doing right now, then another thing we could have done is we could have kept the parameter, but then switched on 2 different large loops in the outside. That'd be complicated. We could still reuse R8 or R9, but only after doing the dispatch. I think this is good. We put the dispatch into the C++ code. Super interesting, actually. My brain's still like, ooh, that's kind of weird. Like, how do you make it easier to control where the dispatch happens? Interesting. Anyways, okay, let's do this. So we want to process the digit. In this case, that just means emit the digit exactly as it is. So we're going to move into our output pointer. That is RAX. No, wait, that's our input pointer. Where's our output pointer? R8. Move into our output pointer, R8. That's where I use R9 once. R8. Move into R8, the value of D, that's RCX. And then we can inc R8. And then we can filter. So that's how you process a digit if it's single digit, right? That's very simple. If we were doing 2 digits, it would get more complicated. So that's why I wanted it to be like a separate case or a separate path entirely, because I wanted to be able to get the simple one here, and like they'd be like 3 paths, right? There'd be is it 1 digit, is it 2 digits, and if it's 2 digits, the complicated stuff inside there. Yeah, this will just keep it all a little bit simpler, I think. And we can do it with fewer registers, so I can use R9 if I need to. I'm still trying to justify it in my head, but I think I like it. So that'll just move us along. Eventually, we'll get to the one passed last, and the loop will be done. And then we just need to fill out the rest of the result struct. So the result struct is sitting in this RAX pointer now. So let's see, we want to give result.count should be equal to putter minus memory. So we can get memory. I don't know where putter is. Putter is in R8. So where is memory? I think memory we ditched. Memory was originally in R8, but then we stuck it here on the stack. No, we stuck it here in RCX. No. Oh, okay. So this is. Yeah, we stuffed it into the result. Okay, this is a little confusing, but I think who is free? R9 is free, I know. RDX we need, right? No, RDX is done. RDX was our one pass last. Let's use RDX. AB 10939, etc. This editor is forcoder. I wonder. Nah, it's a long shot. Once upon a time, I think there was probably a bot in this channel that would have answered to that. There you go. I sent you a link. Okay, so I want to set RDX equal to the memory. So the memory is in RAX now, right? The thing pointed at by RAX, because that's our return pointer. and we stuck at the very beginning, we took our return pointer and we stuffed it with the memory pointer for later. So now we can get it back, and then we can do putter, which is R8, minus that. So we want to do sub R8 RDX. So now R8 contains the count instead of putter, and now I want to store that into RAX plus 8. Because that's our return pointer, so I'm taking the count, which is in R8, and sticking it into this return point struct. Okay. Then we want to do result dot, let's see, line count. That we can just get from line count, which we've been doing up here. So here we did like memory equals D, memory plus equals 1. And then this is like memory putter actually. And here we did memory putter minus memory. I could call, instead of memory, I could call it out. That would be a good name. There's out. So then we start treating R8 as outputter here. We output to it, we increment it, etc. Here we subtract R8 from the original memory, or like the original out base address to give us the count of how many bytes we emitted. Here we just want to move into RAX plus 16 the amount in our line count, which is R10. And these don't need num digits anymore. Okay, so that's good, but we still need to write the 2-digit version. For now, what I'm going to do is I'm just going to copy paste the 1-digit version, and then we'll fill that in a minute separately. 2dig, okay. Whoops. 2dig. Glad we have that error checker there to make sure I type the same name in twice. Wouldn't want to mess that up. All right, let's take a look now in the debugger if we get an array that matches like this string from this. Count 1000, line count 20, and can I see like, how can I do this? Data.v, give me, I'll look at that 1000 elements. I'm gonna put this side by side with, where is my for coder? Okay. 73167. Okay, let's take a look at, if there are 1000 elements and 20 lines, then it's going to be like, I'm so bad at math. 1000 divided by 20, 50. So at around 50, let's make sure, 491949 349698. Okay, now the last digit should be 3450. Oh, it stopped at 500. Why did it do that? Don't know. But that's okay. We'll just look ahead this way. 963450. Okay, it's all looking good. All right, so that should work for this one, and that should work for this one, right? So let's try that one real quick. Okay. Again, let's just peek here. What's in the data? 100 lines with 5,000 elements. That makes sense because I said these were 50-digit numbers on each line. So all I want to do is real quick just make sure that a few of these make sense. So data.v100. Let me see the first 100 elements. 3710. Yeah, it looks like we got it. 0250. Did I do my math wrong? 50. Oh, right. I just want to see the first 50, not the first one. Okay. 50-digit numbers. 0250. Yeah, okay. Okay, so I think that for 1 digit, it looks pretty solid. Now, for a 2-digit loop, things have to be a little bit different. So when we're processing a digit, it won't just be a matter of emitting it necessarily. First, what we have to do is accumulate it into, we're gonna have like state going back and forth here. It's gonna get complicated. So process digit, this is in the 2-dig case, right? I'm not modifying the wrong one. Yeah, 2-dig case. So we wanna have like a dig count here and set it to 0. So that'll be in R9. Remember, R9 is free now. And so in R9 we have dig count, and then when we go to process a digit, we multiply the accumulator. We need an accumulator as well. So accumulator equals 0. R10 R10's taken R11. Do I need to push R11? No, R11 is also volatile. Great. So we have just enough volatiles because we didn't merge these two loops together. I guess RBX. Wait, RBX isn't. I can't remember. Is that one volatile? I don't know if I've ever used RBX. RBX. Show me about RBX. Non-volatile. Okay, that's why I've never used it. I just haven't happened to need that many, and I've been using the R-numbered ones because they're easier to remember than RBX. It's kind of confusing. That's the only one of the lettered ones that is non-volatile. Okay, so let's go with this. So R11 is our accumulator, R9 is our digit counter. And so whenever we come down here, we're going to do accumulator plus equals D. So we add into the accumulator R11, whatever's in RCX, that's where we put D. And then we're going to do accumulator times equals 10. Actually, we do that first. So I mul our accumulator by 10. So the reason for that is every time we process a digit, we want to take what's already there and make it bigger. So like when we process the 2 here, the first thing we see will be the 2, but that'll actually be worth 20. So we multiply by 10 at every step so that whatever's already been accumulated then gets shifted up 1 digit. Then we add in the next digit. And then what we are going to do is we're going to increment our dig counter. Okay. So dig count plus equals 1. Inc dig count. Dig count is in R9, right? Yep, dig count's in R9. And then if R9 does not equal 2, we can go to loop 0 next. So compare R9. R9 is our dig count to 2. Jump not equal to loop 0 next. So just keep doing your normal thing if we didn't get to the number 2. But if we got to the number 2, that means we've consumed 2 digits. And so, yeah, so this one could be like the end dig. So it makes sense. I see. So like if we were going to do 3 digits, we would use the same loop. But for 1 digit, it was a lot more onerous to do all this, right? It took 2 instructions to process a digit before, and now it's all of this. But if you're going to do 2 digits or 3 digits or 4 digits, it's all kind of the same except for this guy right here, and you could replace that with another register. We could reserve one register. Excuse me. We could reserve one more register somewhere. We could squeeze it out or use a one of the non-volatile registers for our digit counter, like max value there. And it would all just kind of work then. But anyways, we're going to keep going with 2 built in right now, because that's the only cases we know of so far. I guess what we could do is say over here in Euler data from text, let's just assert that num digits equals 1 or num digits equals 2. Those are our handled cases. All right, so if we're not done processing, then go here. Otherwise, we'll actually do an emit. So this looks a lot like the first process digit now. We want to do this, which is outputter equals the accumulator. So R11 is our accumulator. R8 goes out, gets incremented, and then our accumulator gets set to 0. And then we fall through like normal. So here we still emit, but instead of emitting the digit directly, we emit the accumulator and then clear the accumulator. I guess we also need to set the dig count to 0. R9. Yeah. So you can see it's like 1, 2, 3, 4, 5, 6, 7 extra instructions to handle 2 or more digits. Well, actually, it's to handle exactly one value. Like, to handle exactly 1 digit is 2 instructions, basically these 2, right? That's what it takes to handle 1 digit. To handle 2 digits, a fixed number, just a fixed 2 is these. It would be the same number of instructions to handle an arbitrary number of digits, but then we would need to allocate another register to it. So you can see how specializing gets you simplicity and performance from that example, which is kind of cool. Anyways, let's test that one out. So Euler 11, and let's take a peek. So when that runs, we get data. We got 20 lines and 800 elements. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, you know what? I didn't tell it to run the 2. Boom. 400 elements. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. All right, so yeah, this is like a 20 by 20 grid. So we get 400 elements. Let's take a look at those elements real quick. So data v400, should be able to show us those. 8, 2, 22, 97, 38, 15, 0. Yep, this looks good. It figured out 48, 67, 19, 89, 1, 52. Yeah, okay. So there we go. Part 1 done. We have a parser. Next up, let's try to solve one of these problems. Let's start with the easiest in the set that we were looking at. So this one. I'll take a quick minute to drink some water and rest my voice for a minute. I'm trying to stare at this and see if I can spot the 9989, but I don't actually see it. Where's the 9989? It's like a completely and utterly abstract word search. Except that I know it goes from left to right, and it can also wrap. Six, 9, 5. Where are you? 9, 8, 9, 0, 9, 9, 7, 2, 8, 8, 8, 8, 6, 9, 1, 9, 4, 4, 4, 4, 4, 4, 2, 9, 2, 6, 1, 7, 8, 9, 8, 2, 2, 2, 6, 8, 9, 9, 6, 9, 9, 8. There it is. 9989. So, this problem says the 4 adjacent digits in the 1000 digit number that have the greatest product are 9 times 9 times 8 times 9 equals 5,832. I've highlighted right there where the 9989 is. Find the 13 adjacent digits in the 1000 digit number that have the greatest product. What is the value of this product? So we wrote the parser. It can grab this text and turn it into a one-dimensional array of bytes. So all we need to do now is figure out how we're going to find 13 adjacent digits with the maximum product. So first of all, let me do a couple of calculations here. If I take 9 to the power of 13, how does that compare to... Yeah, so we're going to need a 64-bit number to hold the maximum, but that'll be fine. We can handle that as multiplication in 64 bits. Because 9, which is the highest possible value, to the power of 13, is still fits within a 64-bit number. So the direct thing we could do is basically say, start from the beginning, and scan each element. So like we could scan this one, and then we could scan this one, and then we could scan this one, and just grab 13 elements each time. I'm not sure if I'm highlighting 13, but something like that, right? Scan 13 elements, multiplying them together, and then, keep track of which one, keep track of a max along the way. I think that's basically what we're going to do, except we'll do one optimization here, which is we'll start with a product of the first 13 elements, and then if we encounter a 0, we'll just stop there, because the next spot that's worth skipping to is the one after the 0, right? So once I'm about to put in a 0, there's no point in checking any of the things that are going to come before that, or come before that 0. Because until we get past that 0, all of the products will be 0. So we can stop there, and we can resume from here. And then for anything that's not 0, what we'll do is we'll divide out the thing we're dropping, and we'll multiply in the new thing. So I can find an example here. With 4, let me do it with 4 digits. So here, what I would do is I go, that 7's not a 0. So I'm going to divide out that 7, 1 divide, and 1 multiply. So instead of 13 multiplies, it's 1 divide, so divide out 3 and then multiply in 1. Okay, divide out 1 and multiply in 7. Divide out 6 and multiply in 6, and so on, right? And at each point, I get a product of 13 numbers, or in this case 4 numbers, for the spot right here. Once I hit the 0, I just go, okay, stop there, do the same loop again, reinitialize from here. because I can't do division size 0. So I'll start from here, and then I'll do multiply all of those together, test them, and so on and so on. So then what we're going to end up with is at each step we have a value, and we can compare that to previous versions of the value, and find the maximum index. So let's just type that in and get a solution. C linkage U64 Euler 8. So we're just going to write the assembly to do what I just described and call it a day. For this problem, we'll do more problems. I didn't mean to say call it a day in the sense of being done with the whole day. Because, there are other senses to that word or phrase. Okay. There's our data. And then, okay, so Euler 8 is going to have to take an array and a count. And so Euler 8 gets the v and the count like that. And it gives us an answer. And that answer, and I'm looking for the value of the product. So all I need is the maximum product. I don't need the index. I don't need the digits. I just need the product. Printf. Answer. Okay, so I'm going to have in RCX, see Euler 8, and RCX is the array, in RDX is the count, So I'm trying to think of like how I want to phrase this loop. So there's like several phases to the loop, right? First, there's the very outermost phase where we have like a pointer. So RCX is like our pointer, and we need like a one pass last. And the one pass last is going to be equal to, we're gonna say that there's like a constant here. So like we'll say like size equals 4 for now, and later we'll set that to 13. So one pass last is going to equal the array plus the count minus the size plus 1. So why all that? Well, if we were scanning for a size of 1, then what that would mean is we were going to look at this, and that would be one of the products, this, and we'd end up finding 9 would be the maximum product, right? And that means we would check every digit. If we were doing 2, we would do all of them except after 5, 0, we wouldn't check 0 and the next thing because there is no next thing, right? We would check 4, 5, we would check 5, 0, and then we would stop. So when there's 1, we do all of them. When it's 2, we do 1 less. When there's 3, we do 1 less again. So we are subtracting 1 for every time the size of our scan goes up. But when our size is 1, we're doing all of them. So if we just did this, we would have an off by 1 error, right? So this is the one pass last that we want to compute. So let's put that in R8. Let's see. So there we go. That should compute this expression here and put it into R8. Now, what else do we know we want to do? So we want to have a loop. It's like loop 0. And loop 0 says if Yeah, so if RCX is greater than or equal to, so this is if putter is greater than or equal to one pass last, go to done, right? So we're going to compare putter, that's RCX. Why don't we put this in RDX actually? Yeah, I like that better because then we can just add RDX, RCX and ditch the RDX. We don't need it anymore. And then R8 is still free. Cool. We don't need count. Yeah, okay. So compare RCX to RDX. Jump if that's above or equal to done. Here's our done label. Now we're going to use, we need to have RAX be our return register. And so we're going to have RAX be our max. So we're going to say like max equals 0. RAX. So as we're going, we're going to look for opportunities to make RAX bigger. And then when we're done, we'll just return the biggest RAX we found, right? So at some point, we're going to have a jump back up to loop 0. But now the question is like, what do we do in loop 0, right? The loop is kind of like a weird multi-phase loop. If we're at the loop 0 label, actually I'm going to take this out because it's a little bit more complicated than a normal loop. So here we're at loop 0. What we want to do is build an initial scan, right? So this is where we're going to scan across the next several elements to build up a product. So we need a place where we can keep that. We'll keep it in R8 and we'll use R9 as the scanner. So this is going to be like the major section. So here we go. We're going to have putter S or putter P equals putter. So mov into R9 from RCX. There's our putter P. We're going to move into we'll call this, I don't know, P equals 1, and that'll be R8. So we have a 1 in R8, we have the putter P in R9, and then we're going to do how many steps? Exactly 4 steps. So we could just like do 4 steps by copy pasting the code, or we could do a loop with a counter. If we do a loop with a counter, we got to allocate a register to being our counter, or yeah, okay, so we'll do this. We'll say opal P equals putter plus size. So we want to move into R10 from RCX, add R10 4. So now we should be able to do loop 1. And loop 1 says if, let's see, putter P is greater than or equal to 1 past last P, go to loop 1 done, right? So compare, and really we don't need to do this. Why don't we do the test at the end of this loop? So what we're going to do at each step is we're going to go at each step, we need to read out of putter P. So let's see, who's free? R11 is free, so we're going to grab D equals putter P to R11 from, what's putter P? R9. So D is now in R11. That's the new digit we want to do. We want to multiply that in, so P times equals D. I mul R8 by R11. Then we want to increment, yeah, go to loop 1. Okay, Then we want to inc, let's see, we want to take d, or putter p plus equals 1. That's R9. And then we want to compare R9 to R10, jump if below or to loop 1. So if putter p is still less than this, we go back up. Otherwise, we flow down and we're done with loop 1. So that's it, except that this doesn't detect zeros. So what we want to do for detecting zeros is kind of a little bit of extra work. If d equals 0, go to R8 equals putter equals putter p plus 1. Yeah, let's see. I want something that'll be like, yeah, we'll just say like go to loop 1 skip 0. Okay. Compare d. This can be like a test d. So R11, R11. Jump if that's a 0 to loop 1 skip 0. Loop 1 skip 0 needs to work like spaces. Okay, needs to work like this. Loop 1 skip 0 says, so R11, so set putter equal to putter p plus 1. So putter p had a 0, so we want to skip that. Move into putter, that's R9 from R11. Inc R9 by 1. And go to loop 0. So that's what happens if we find a 0. Now we can say what happens if we get to the end of this loop. So this is the build an initial scan part. R9 and R10, R11 are all free again. R8 contains the result of our scan. So then we want to do loop 2. And what loop 2 will do is say, first of all, if R8 is greater than if P is greater than max, max equals P. That's what we want. So this will be compare P, which is R8, to max, which is RAX, and then mov, conditional mov above, move into RAX, R8, right? So if R8 is greater than RAX, move R8 into RAX, conditional move. So that's the part that does the setting of the max. And then what we want to do is say, okay, if now we should be able to increment P. Okay, first what we're going to do is we're going to say P divided by whatever is in putter, right? Whatever is in the putter, we're going to divide that out. So we can read out of putter. Putter is in RC. Oh, putter equals putter P. I got this wrong. So putter P is 9. RCX is putter. Yeah, okay. So we want to read out of putter. We're going to put the result of that read into R9 because that's free here in loop 2. R9 from putter, RCX. This is a single byte. So byte putter. We grab out of that, put it into R9, and then Oh crap, if we're gonna do divides, then RAX is a bad choice. Yeah, so our max can't go into RAX, so we're gonna rearrange some things. So let's see, our max will go into R9. Oh, we're using RDX too. Yeah, that's mistakes. Gotta stop making that mistake. So if we're gonna do a divide, we need RAX and RDX to be free. So let's free these up. Let's move into, we'll just go backwards from the top. R11, we'll get RCX. We'll add RCX in there. We'll subtract 3. R10 will be our max. So our CX is fine to be putter. R11 is our one pass last. Here, R9 is fine, RCX is fine, R10 is not okay. So you'll be RAX. RAX will be our one pass last. We can make you RDX. So putter P will be RDX. And then P can be RH still. Yeah, that's fine. 11, 10. We're using RDX and RAX here. Good. R8. Good. So loop 1. So this is the build and initial scan part. From here down to here. Advance the scan. One step at a time. Okay. So here, R11 is already allocated for being our one pass last pointer. So we can't use that. RX and RDX are allocated R8, but R9 is free. So our putter P is RDX. This should be R9. These should be R9. This should be R9. Our putter P is RDX. Putter P is RDX. One pass last P is RCX. Jump back to loop. Jump below. So R8, R9, RDX is less than R. That should be RAX, right? RAX is the one passed last. P. So for building P, we have putter P in RDX. Boom, boom. We have P in R8, D in R9, and one pass last P in RAX. Okay. For this, we compare. Okay, so our max is not RAX. Our max is R10. Like that. P is still in R8. So what we're doing is we're reading into R. Let's see, R9 is free. But we actually are going to divide with this. So this is our RAX. We need to clear RDX. So technically this isn't quite right. So R8 is the thing we want to divide by. So we're going to move, this is kind of weird, move into RAX from R8, move into RDX, or clear out RDX. So there we've set P up for the divide. Now we want to set up, let's see, R8 needs to get recycled. So RCX is our putter. We're going to read out of that putter and put the result of the read into R8. And then we can do a divide. Like so. That will put the result of the divide into RAX. Now we want the result of the divide to move back into R8. So that gives us R8 is still our p-value, and we've divided by the putter there. So there's our divide part. Now what we want to do is, if we've done the divide, we want to increment our putter. And then we should test the putter. So it's the same test we did at the beginning of loop 0. If our pointer has gone past the has reached the one past last point, then we're done. Otherwise, we're going to multiply in whatever is there. So this is going to be, let's see, who's free now? RAX is free. So we're going to say p times equals star of putter plus size minus 1, right? So putter plus size would give us the thing one past the last of what we're actually trying to, like, if we're trying to scan 4 elements, then we're scanning elements like, 0, 1, 2, and 3. We don't scan we don't actually multiply in element 4. That's not the final one. So we've done the increment on the pointer already. So now we want to multiply in the thing that's at size minus 1, the last element, not the thing past the end of the current scan like window, right? So we need to do this read first. Let's move into RAX. The value we get from, it's going to have to be a 0 extend from the byte pointer that you get by looking at the address in RCX plus 3, right? Size is 4 minus 1 is 3. So we read that byte, put it into RAX, and then we're going to multiply that into P, which is in R8. So RAX gets our value from this dereference. R8 gets the value from the multiply. And now we go back up to loop 2. So we once again want to test the max because we have whenever we go to loop 2, it's either because we just finished building an initial scan or we just finished incrementing the scan. But there's one thing we didn't account for, which is what happens when this, when this turns out to be a 0, right? So that's going to be like this. D equals this, and we need a, if D equals 0, then go to loop 2, skip 0. So here's how we skip zeros in loop 2, basically, is the idea. So we need to test RAX, jump if that's 0 to loop 2, skip 0. Loop 2 skip 0 means we take pointer and we add in size minus, let's see. So if we found a 0 here, it means that we were scanning along and then we were about to consume this. So if we're at this position, we want to skip ahead by exactly the whole amount, right? So we did an increment of P. We had been here. Did an increment of P and we found here. So there's our P value. We want to go up 1, we want to go up 4 whenever that happens. So add to our putter 4 and jump to loop 0. It all assembled. It'll be kind of surprising if we got all that right in one try, right? But let's see what happens. So if I run this, I get that. That seems way too big. The answer is supposed to be 5832. So let's see. What did we get wrong here? Well, it's kind of hard to say. Let's just walk through it. That seems like the only thing that's going to work. Here's the beginning of our problem. Got the right text, right? What's going on here? Okay, Euler 8. RCX is our array. RDX is our count. Very good. 500 elements. XOR 0. Okay, so let's start thinking this through. So putter is getting compared to the one passed last. Should not be done yet. It's not. Okay. Build an initial scan. So here we're going to start scanning. So we're setting RDX to be our putter P. Let me look at registers here. RDX. Okay. RAX is the one passed last for the putter P. So that's 4 more than that. Okay, very good. And then P itself becomes 1 to get started. Then in a loop, we are going to move into R9 from, that's a mistake. That should be a single byte read. Okay, looks like I remembered that in the other places. So let's start by just going, no, it's still too big. It's more reasonable, but it's still wrong. So let's look again. Okay. P. That is not 0. So we're multiplying that into P. Let's take a look at what the first 4 digits are. 7316. So we should see those all getting multiplied. Somehow R9 seems to have gotten more than that. That doesn't seem right. Let me double check. Oh, okay. Well, thing number 1. Gotta set this back to a 1. Okay, now it's crashing. Okay. Euler data from ASM. Did it just crash in the Euler data from ASM? No. Hold on. What's going on here? Boom. F10. Okay, there we go. So the data comes back looking good, right? Data V, give me the first 100 elements. 7316. Okay. Now, we come in here. When we read, R9 should have gotten a 7. R8 becomes 7. We ink our DX. We're not done yet. Back to loop 1. We read R9. We got a 3, 7, 3. 7316. R8 is 7 times 3? That shouldn't be 15. What? Am I crazy? 7. R9 contains 3. R8. Oh, that's hexadecimal 15. Got it. Fair times 1. Nothing changes. Times 6. 7136. Is that right? Yep. 7136. So we get 7e. Let's grab the calculator from Windows real quick. Programmer. In hex, we just saw 7e 126. So what if we divide by 7, 6? Yeah, okay. We're going to put this here so we can see it in decimal. Okay. So that loop is done now because rdx reached the same value as rax. Then we compare that to max. So max should currently be a 0, and then it should become, there we go. There's our new max. We then go, hey, can we divide out the 7? And what we get left over with is the hexadecimal 12. So that's 18, that's 3 times 6, yep, that's good. We increment RCX, RCX is our main pointer. We compare that to our 1 pass last, it's fine. We move into RAX the next byte, so yeah, 7 is the right thing. Go multiply, so we're not done with, we're not skipping a 0 here. So R8 gets multiplied by 7, it goes back to the same value it had. So that doesn't actually change anything. We divide out now, what? What are we dividing out? A 3. So then we read out the 1, is that right? Yep. So now we just have 1 times 6 times 7. So that's what, 42? Yep. Very good. So that seems good, which means the only way it could have gotten a bigger result than the actual answer is if it hit a bug that makes P get bigger down a path besides the one we're looking at. So let's look and see if we find either of these paths. Eventually we should find this path. So RCX now goes up by 4. Let's take a look and see if we can look at the next few values that are visible here. So when we do that, we go from 1330 to 6294. That's the first 0 we found. 1330 to 6294, right? Yes. Okay, good. So loop 0, we're going to look at comparing this to that. That could have been broken. And then we go right into building an initial scan. So RDX gets the current putter. RAX gets the current putter plus 4. We move a 1 into R8. So we abandon whatever we had because we're skipping past a 0. We move into R9. First the 6. Then the 2. This becomes 12. Then the 4. And then the 9. Come over here. We're going to divide out the 6. Becomes 2 times 4 times 9. Yep. So that's good. Do we ever hit? There we go. We hit this one. So if loop 1 skips 0, then RCX, which was right here, whoa, okay, that's got to be wrong. Loop 1 skip 0. We tested if D was 0. Okay, right. So that's not right. What is putter P? Putter P is RDX. Now we just get a 0 as the answer. How is that? Okay, so the answer is in one of the registers, it's not in RAX. Where did we keep max? We kept max in R10. So at the very end, we want to move R10 into RAX so that the return register has our answer. 5832 is the right answer for 4 digits. Let's try size equals 13 now. So wherever size shows up, I just need to change that constant. Excuse me. boom. All right. Let's see if we've got an answer. Yes. All right. There's one down. 2 hours in, we wrote the parser, and we wrote one solution. Okay. Let's tidy up from that one. Euler 8 is done. Euler 8, we'll get rid of the text for that one. Euler 8. All right, let's try Euler 11. What's this one? In the 20 by 20 grid below, 4 numbers along a diagonal line have been marked in red. The product of these 4 numbers is 26 times 63 times 78 times 14 equals 1,788,696. What is the greatest product of 4 adjacent numbers in the same direction, up, down, left, right, or diagonally, in the 20 by 20 grid? So they want us to scan the whole thing, but not just what we did before. Like, we could turn this into a one-dimensional grid. It would literally be the same problem, except now looking for 4 instead of 13, right? It'd be trivial, except that the parser would be a little different. But actually, the problem's a little different too. Because once we've figured out what the grid is, it's going to be like, here's one possible product, and here's another possible product here. So we could turn this into, maybe I should have saved the problem we just did. I could turn this into a bunch of instances of simpler versions of the problem, right? So we could say like, here's, do this with the 4-digit version of what we just did on that row, and then do it on this one, and do it on this one, and then on this I would do the same thing with the columns. And the only trick I'd have to do is, in order to like handle this column here, I'm highlighting the whole thing, so I can't just highlight I can't like highlight just the column I'm looking at here. But in order to just look at that column, I would just have to give it a stride as a parameter, right? And same thing with the diagonals. I would say like, look, we're going to end up looking at, for instance, for this diagonal, just use a stride of 21, and you have, I count out however many are along the main diagonal. I guess it would be 20 on the main diagonal, and then I have to just manually put in the calls for each of the rows, columns, and diagonals. I feel like that's what I want to do, because I don't see how this is a different problem. So let's just maybe we could save this function instead of throwing it away. What is this function doing? It's doing I don't know. We're just gonna adapt what we've got though. That seems like the right thing to do. So let me call this Euler 11 now. So let's see, Euler 11 takes in an array, a count. We actually have to adjust that, so that's a little bit wrong. We need to throw in a stride. This would be like Euler 11, or Euler 8, strided. I don't think that this is reusable. It just happens to be like a very similar problem shows up twice, right? And Euler 11 is like x, y, right? And Euler 8 strided, you give it an array and a stride and a count. Okay. So let's see, rdx got changed to r8 there, so there with the count in, change the size back to 4. Okay. So R8's our count. I'm gonna just push something onto the stack here. RSI will be our stride. And then we'll restore RSI right there. Okay, so RSI is our stride. Now, what can we do with all this? So the only thing that changes when we have a bigger stride is that well, I think it's just gonna be anywhere where we did inc. Now we're doing plus stride, right? Add RSI. So here during loop 1, when we're building the initial, we're going to increment by the stride instead of by a fixed 1. Yeah. Here, when we're doing loop 2, after we do the divide out, we're going to increment. Okay, I see. So it is a little bit more complicated than I thought, but not by a whole lot. So we're going to increment RCX by the stride. Are there any other inks? RCX. Yep, so this is, we take putter P and we add in an entire stride. And then this has to be size times stride. So that will take a little bit more work to calculate. We'll need to figure out what's a register that's free here. So in loop 2, RX, it looks to me like in loop 2, R9 is totally free. We did use R9 up here for stuff. That's just loop 1 stuff. Loop 0 does, yeah, loop 9 is free. So here what we'll do is we'll say, okay, first of all, move into R9, the stride. Actually, we can kind of cheat here because we know size is 4. So we can set putter using LEA. RCX is going to be RCX plus 4 times RSI, right? Okay, there we go. No extra register. Just a little bit of, I think I like to write it this way. So that 4 is our size, the stride is RSI, RCX is the putter, and it goes back into RCX, the putter. Okay. So there's Euler 8 strided. I think that's literally just about it. The only other thing is this right here is wrong because we want to do all of this times the stride, right? So what I think we'll do is we'll rearrange things. Originally we were adding in RCX early, but let's not do that. Let's instead first calculate this and then imul R11 by the stride. So here we're calculating this product. Here we're calculating count minus 3. So count minus 3 times stride, and then finally we add in the array. Yep. That's all good. So what else? I think that's it. So Euler 8 literally just, or Euler 8 strided literally just as a helper sitting here. And then what we'll do is we'll have Euler 11 is a thing that you call with v, and then you want to give it the x and the y. So the x is going to be count divided by line count, and then the line count will be our y, right? So that should work, except we don't have an Euler 11 defined. So there's our final goal here. To solve this one, we just need to write that. So that's RCX is our memory or data or whatever you want to call it. RDX is our x dimension. R8 is our y dimension. Okay. I'm gonna take a 5-minute break, 5-10-minute break, and when I get back, we'll write this Euler 11 solution. See you in a little bit. Alrighty. So, what we want to do now is basically break this up into several parts. So let's first call this on rows. So let's call it on the first row. So what we're going to be calling is Euler 8, strided. And we need to set, we obviously need a return instruction. We need to set RCX to the data. It's already going to be there. Let's do this real quick. We need, like, since this is a function that calls another function, we're going to want to just remember all these parameters. over the boundary. So let's move these things over into non-volatile registers. 13, 14, RDX, R8. R12 gets data, R13 gets the X dimension, R14 gets the Y dimension. Okay, now we want to call this, now the strided function, we want RDX to get the stride. So the original stride is going to be 1, and the count is going to be the X dimension, right? So if we do that, we should get an answer. Whoops. We should get an answer. Oh, we didn't. What happened? Let's take a look. What is going on? Why doesn't the debugger show me what happened? Oh wait, first of all, that's not even the right data. So let's make sure that that part makes sense. How about that? Data is 20 by 20, and data.v, the first 20, 8, 2, 22, 97, 38, 15, 0. 8, 2, 22, 97, 38, 15, 0. Okay, yeah, those are a match. So, count divided by 20, 20. Yep, so all that looks good. And if I step into there, I'm going to save those for later. I'm going to start using them like this. 13, 14. So I'm going to say RDX becomes 1. That's the stride. R8 becomes 13. That's the count. And we step into that. That's going to put its stride into RSI for reuse. And presumably, when this RSI contains 1, this should just eventually terminate, right? It does. So now RAX is 4026A8. We come back out here. Exception thrown. Here we go. These need to be pops. Okay, so that 4204200 should be the largest product you can get from 4 things in the first row. Right? 4204200. So like probably can't have that. Yeah, that would be big, but that gets paired with a 2 and an 8 or a 2. Yeah, so probably like right here. Or maybe, yeah, maybe right here. Let's try those and see if that makes sense. 12 times 50 times 77 times 91. There it is. That's the one. So yeah, that found the max in the first row. So now what we could do is call it on each row, and we could call it on each column. So let's start by trying it on a column. So call on, let's do this a little bit more sort of robotically, a little bit less, yeah, just do a little bit of extra typing in there. Okay, so the stride will become the x dimension, right? Whatever the x dimension is will be our stride, and our count will become the y dimension. $40. So it says along this column, 40 is the best it can do. That doesn't sound right. Because like that right there is just definitely more than 40. So what happened there? You know, what happened? We started off in the same, yeah, started off at data there. We would have been striding by 20 going, okay, let's just take a quick, look at that. So when you try to call by column, the columns version, boom. So your stride turns out to be 20, which is hexadecimal 14. And then, let's see, you grab the first 4, add RAX4. That can't be right. So anywhere where size showed up, I should have been incorporating the stride, is basically what it comes down to. And I didn't do it in 2 spots. Okay. So this here should be size times stride. So RAX should be, let's take RAX should get the value of RCX plus 4 times RSI. That's what it should be. Boom, boom, right? So RCX is this guy. Size is this guy. Stride is this guy. So this is tricky because this needs to be size minus 1 times stride. So how can we do that? We can't very easily cram all of that into one memory address lookup, because while we could do 3 here, we can't do 3 times stride. Stride can only be multiplied by 4. Now what I can do is I can multiply by like stride plus 2 times stride. I can multiply. One of them can have a multiplier of 1, 2, 4, or 8, and the other one has to have a multiplier of 1. But I can't have 3 registers either, and I need RCX in there as well. So I need to look and see, do I have a free... Yeah, I do have a free register. I could use R9. So R9 is going to get RSI plus RSI times 2. So there's RSI times 3 put into R9. And then we're going to take that and add it to putter, which is RCX. And that should be better. So let's see. I want to first look at the result from this one again. So that's what we got before. Good. And then boom. Ah, that looks better. 450536. 450536. 536. 536. So can't be this one. It's gonna be something. 66. 8 times 9 would be 72. 8 times 4 is 16, sub 7. That'd be 2, 14, 16, 2, 4. Okay. Is it 81, 52, 22, and 24? $52, 22, 24. No, it's too small. Is it 6 times 6 times 8? No, that's not. 8 times 9 times 1. 9 times 2 times 2? Ah, there it's, that's what it is. 49 times 81 times, wait, I think I just did this one. 52 times 22 would be 45. Oh, I must have typed it in wrong because that looks correct. 4540536. Yep. Okay, so that gave me the column. And then presumably, if I gave it x plus 1, it would give me the stride along the diagonal. Now, the only thing I have left to do is I need to call this multiple times, and for each one, I need to like test it against a max. So let's set aside another non-volatile register for that purpose. And this time I'm setting it aside, wait, 12, 13, yeah. This is out of order. 15, 14, 13, 12. Okay, 12, 13, 14, 15. Got it. So 15 is going to be our max. And then we'll just do after any one of these calls if RAX is less than, or if R15 is less than RAX, R15 equals RAX, right? That's the idea. So if max is less than the return value, max equals the return value. Compare R15 to RAX. Conditional move if below R15 into RAX. Okay. So I do the call, I do the conditional move, and then at the very end, we return that max value. Okay. Boom, on columns. Okay, so now what we want to do is we want to visit all of the rows. So there's one row. Okay, so we need a loop. Oh man, do I need more registers? I mean, one way I could do this is just copy pasting it, doing it literally by hand. It'd be kind of annoying. Nah, I don't really want to do that. So let's grab another register or two. Let's see, we're going to do RSI and RDI, I think. Okay, so in order to call it on rows, what we want is first I equals 0. Then loop rows if I is greater than or equal to y dimension, go to loop columns, Okay, so that's good. If I is good, go to loop. Oh, I gotta write that. So compare I to R14, jump above or equal to loop columns. So we just go to the next loop. Otherwise, we want to do a call here, but this should be Euler 8 strided with let's see, R12 is data plus I, and then 1, and then X dimension. Right, so there's our count, there's our stride, and there's our starting position. And so we want to calculate that. So R12 isn't good enough. What we got to do is do RCX gets R12, and then add RSI. The I value. And then we do the compare, we do I plus equals 1, go to loop rows, right? So inc RSI, jump loop rows. Okay, so there we go. There's our loop for rows, loop for columns. Call on columns, I equals 0. We might not end up needing RDI, I'm not sure yet. I think I might need it for diagonals, but we'll see. RCX, RDI, blah, 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 call. So yeah, we want to say if I is greater than or equal to the, so for columns, we go across the X dimension. Go to loop diags, compare RSI to R13, jump if above or equal to loop diags, Here we're calling Euler 8 strided with data plus I times the X dimension, because that's the stride, the X dimension, and then a stride, oh, and then a width of Y dimension, right? So this is X dimension and Y dimension already, but this is not quite right. We want to move into RCX, the value of RSI, the I value. We want to multiply that by R13, the X dimension, and then we want to add that to R12, the base of the data, right? So that gives us this expression. This and this fill out these two parameters, and then we do this, increment, I plus equals 1, go to loop row, loop columns. So there's an issue. Begin loop columns. You can't go straight to loop columns, because you gotta have somebody clear this to 0 first. Begin loop columns. So this will actually have to go to begin loop diags. So let's see if that is all looking good so far. Begin loop diags. Begin loop diags. Okay. Okay, so it found one, but it didn't look at the diagonals yet. It looked at all the rows and all the columns. Now we want to look at the diagonals. Now the diagonals are a little bit trickier because their count doesn't stay the same. This one has a count of 20, but this one and this one have counts of 19. This one and this one have counts of 18 and so on. This one and this one are the last ones that actually work at all, and they have a count of 1. Well, 4, but yeah, they have a count of 4 because the Euler 8 part will handle the number of actual tests to do. We have to tell it the actual length of the diagonal. So the length of a diagonal is going to be, let's start by doing the diagonals along the top, right? And then we'll do the diagonals along the sides later. So here, I equals 0. All on diagonals, okay? And then the loop diags looks like this. If I is greater than or equal to I plus 4. So we're going to go to begin loop diags 2. So how do I want to pull that off? I'm going to need to have a way of adjusting our system. When I look at these loops here, I can use any volatile register I want. RCX is going to get RSI. RCX is going to get RSI minus 4. RCX. Versus Y dimension R14. Wait, what am I doing? Minus 4. RSI plus 4. RSI plus 3 is greater than or equal to that. RCX compared to R14, then begin loop columns, begin loop diags 2. So there's loop diags. Oh, you know what? There's not just diagonals this way, there's also diagonals that way. Oof. This is an annoying problem. Okay. Well, so there's 4 diagonals. We'll just power through it real quick here. We have all the building blocks we need to get it done. So let's just grab, let's see. Grab all of these. We're currently doing diagonals. Negative direction. Let's say like negative slope. Negative along top row. Okay. So we actually want to test this like we would test that. Why don't we do along left side? We'll switch this up. So along left side, so it's going to match the rows here. We test against Y dimension data plus okay, yes, we want to call all of this in basically the same way, except this part is different. Data plus I is the same. The stride, instead of being 1, is x dimension plus 1, and the total length is, let's see, we're counting on, okay, so it's going to be, when we go up here, we're saying like, why does it become 19? Well, because the Y dimension cuts it off. So the Y is getting larger here, so it's max x, like the x dimension minus our x coordinate, it's the minimum of the x dimension minus the x coordinate and the y dimension minus the y coordinate, right? So this is min of, it's so annoying though, because like recomputing this every time. I think it's just easier to do it that way. I mean, we're hard coding in that we know that it's a 4x4, like 4 wide. So maybe I should just say we're going to hard code in the fact that we know that it's 20 by 20, because that'll make this make our life a lot easier here. X dimension and y dimension don't even get passed. X dimension is 20. I times x dimension, y dimension, x dimension, let's see. Theta plus I, x dimension plus 1. So x dimension plus 1 is 21 in RDX. X dimension. Okay, so now the count, well, hold on, I just did x dimension. I need to do y dimension still. 20. Yep, 20. Y dimension 20. I greater than or equal to y dimension, x dimension. Okay, so are there any lingering uses of R14 or R13? Just this one. Okay. So the count isn't actually going to be 20. So we have a stride of 21. We're going do. The actual count is going to be 20 minus I, right? So that gives us 20 minus I in our third parameter, call Euler strided, and that should do it. Euler 11, we're no longer passing x and y because we know that they're 20 and 20. That's too complicated. All right, end that task. Some kind of infinite loop. Let's go double check the code, figure out what we got wrong there. So this is jumping back to rows. This should be jumping back to loop diags. So what I want to see is real quick. If I took all of this out, what were we getting before? 1, 3, so 13 million. And then we look at the positive diagonals along the left side, or the negative diagonals along the left side, and we get 32 million. Okay, so it did just find a bigger result. Alrighty, so let's look at negative diagonals along the top. So I'm going to copy the rest of this loop again. So now we're going to go I plus 3 less than x dimension. Yes, good. Diags 3. Still starting by x dimension. Okay, to go along the top. Wait a minute. wait, so that was along the top, because I was doing data plus I. Okay. So this was along the top. Data plus I, x dimension of 20, x dimension plus 1. So this is going to be along the left column. It's going to test against y dimension, which is 20. It's going to have a stride of 21, but its position is going to be the same as if we were doing wait, when I did rows, I just did all of this wrong. This is actually testing column offsets. This is testing row offsets. Yeah, let's fix these. So this should be I times x dimension, and this should not be. Columns begin at data plus 1, data plus 0, data plus 1, data plus 2. Rows begin at data plus I times 1, I times 2, or the stride times 1, stride times 2, stride times 3. So this here is the logic that goes here, and this one is only different in that it doesn't do the mul. Begin loop diags 3. You go to loop diags 2 from here. And okay, so there we go. That found more. Okay, so that's getting better. Now let me just audit all that again. Rows, stride by 1, start at I times a full stride. Columns start at data plus a single step, but they stride by x dimension. Diagonals with a negative slope used an x dimension plus 1, and to go along the top they do the same thing that the columns would do. To go along the left side they do the same thing that rows would do, this thing here. So that is how we index into the array when we're doing negative diagonals starting from this side. Okay, so the last thing to do is we have 2 more diagonal types. To check, here's done. So going back through these, loop diags 3. So yes, this is begin loop diags 3, loop diags 3 for 4, for 3, for done, done, 4. There's the new loop, so that shouldn't change anything because it's the computation we already did. Now, just double check. It might still not change anything. But let's just double check if we run these the right way. So these will be not negative slope, but positive slope. It will be positive slope, which means their stride will be x dimension minus 1, in other words, 19. So there's going this way. They also need to start at 4 rather than doing this plus equal 3 thing during the computation. They just start at 4. Yeah. And we don't do that. We just do RSI. So when that gets greater than or equal to the full dimension, we go to the next one. Okay, so then let's see. In order to do along the top, we're plussing by I. In order to do along the left column, we're plussing by I times, okay. Yeah, to 20 minus I, okay. It's crazy, we have 6 loops. They're all fairly big and doing the same thing. Still the same result, okay. We're gonna plug that in. I have lowest confidence. Yeah, okay. So how can we check our work a little bit, right? How can we be sure? How can we make this easier to verify if it's working? What we could do is we can make the data easier. Right now, we have to work with this data that's like this. So we're going to do sample. And what I'm going to do is with a little macro work, we're going to go boom, 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 boom. And then with a little more macro work, we're going to go boom. Wait, hold on. Macro record. Boom, 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 boom. Okay, so we can very carefully control what the answer should be if we use sample instead of the real text. So now I'm getting an answer of 1. Now, I can throw in a couple of examples here. So it would find 1 if I did that. If I did that, it would find a 1. Okay, cool. So if I did this, would it find a 1? Yes, okay. So that's good. Now let's say I put a 1 in down here. Would it find it? Yes, okay. So it would find that. What if I put a 1 in right here? Yes, it found that. I'm going to put in a 2 now right here. And it find that. No. So the positive slope diagonal starting from here didn't work. 1, 2, 3. Okay. I might have done an indexing bug here. Okay, so we can't find that. That makes some sense. So I said start at 4, but I should probably have said start at 3. That won't explain everything. That should at least let it find this one. Okay. So now why was it not finding this one on the positive slope? Is it not testing that spot? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. It should be testing it. What happens if I put it in the top? It just doesn't see it. So is it just that particular diagonal is not being seen? Now that one isn't being seen either. Okay, so along the top, is that what's busted? That would mean up the side could work and you'd still see... Oh, along the top and up the side are not the ones you need. You need like down the right-hand side. So if I were to put one here, would you ever see it? No. But if I put one here, do you see it? Also no. So this is stranger than I thought. We know they do see it. We tested this one. This one was working, right? If I do this, you'll see it. Yes. if I do this, you'll see it? Question mark? Yes. So when does it not work? $625, 5 times 5 times 5 times 5, yeah. So those are all working. For some reason, somewhere along the way, why don't we do this? I'm gonna make all of these into ones. Wait, sorry. Make all of these into ones. Now I should just see a 1, obviously, and I'm going to try to figure out why, when does, if I put a 2 here and a 2 here, 4 would be the answer, but it only finds a 2. Now if I were to come over here and put a 2 here and a 2 here, it should find the 4, yeah. Okay, so where do I put the 2? There it still works. There it doesn't work. There it still works. We're getting real close. There it still works. Okay, so the first spot where it doesn't work appears to be this one right here, right? This appears to be where it doesn't work. So that's kind of weird. Let's take a look at the code for positive slope along the top. Starts at 3. If RSI is greater than or equal to 20, why is that not good enough? Seems good. That seems like the right thing. 3, 4, 5, 6, 7, 8, all the way up to 19. But for some reason, we're missing 17 and above. None of the math here for skipping the last ones is it being applied. So like we should be doing RSI equals 19 here, right? RSI, go to loop diagonal 3. RSI should reach 19, data plus 19, striding this way. Oh, the length of the diagonal is wrong. The length of the diagonal is wrong. The length of the diagonal should be I plus 1. So that's one issue. Now this I also notice is wrong. This is not going to be able to go, if you do positive diagonals along this and positive diagonals along this, you do the same positive diagonals. So if you've already done the positive diagonals here, you've done all of them in this triangle, so you need to go down this side. So what we need to do isn't just this, right? Because that's these spots. We need to do that plus x dimension minus 1, right? So we could understand this as I plus 1 times x dimension minus 1. So we move RSI into RCX, we inc RCX by 1, then we do the multiply, then we sub dec RCX by 1. And then we do the add. Okay. Okay, so that's now seeing a 2 there. Now I want to see if I switch back to Euler 11 text, did we catch... Wait, hold on, let me double check. The size also... So when I equals 0, we'll be at this position. So that should have a size of I plus 20. No, that should be 20 minus I. You know, maybe it was not about positive and negative diagonals that got that wrong. I equals 0. Big. I equals 0. Big. Shrinking. I equals 0. No, I guess it's right. So the only time, it's kind of weird. The only time the diagonals, when I equals 3, yeah, when you're going along the top doing positive slopes, the diagonal gets longer as I goes up. But in every other case, going down this side, the diagonals are getting shorter. Going to the right on this side, the diagonals are getting... Oh, going to the right on this side, this way the diagonals get shorter. Going down this way, the diagonals get shorter. I also just realized that one of these, we don't need to start at I equals 0. This could start at RSI equals 1, because we've already tested this position. And we could also say the same thing for here. So we started there, and we went all the way up to 20. And we started... Yeah, here we actually want to start at 1 again, and we want to do I plus 3 again. So maybe that's the result that we should be putting in. Looks bigger, like maybe we found more. Yes, all right. That one was a little annoying, so I was worried we'd be stuck on it for a while, but we got it. All right, looking at our progress here, we've cleaned up a couple of the ones we skipped. Now we got this one, large sum. Let's take a look. I'm gonna take a breather for my voice again, but I think that this one might be. Well, we'll take a look. This might be harder than what we can get done in a day, or it might be something we can finish in a reasonable amount of time. So I'm not sure, but we'll take a quick look. It is a parsing one again, but it's different than the first ones. It's not the same kind of problem. So those first ones were like these products in the grids thing, and products in the arrays. Now I think we're totally done with all of these. I still don't think any of that was particularly reusable. Conceptually, I don't know how to describe what it was we were doing. The stride stuff is reusable, like, but not as assembly. Like, there's no way to make the stride concept sort of reusable the way we were doing it, but it's a good idea. You can use the idea again. We can't use the code again, I don't think, very easily. So for this one, work out the first 10 digits of the sum of the following 150-digit number. You know, I said I would take a breather for my voice. I'm going to do that first because I can still feel it. So I'm doing a little number crunching here, and in preparation for this problem. But I'm gonna read this one, and we'll see how much we can do. I might just sort of sketch out some ideas and then call it a night, or I might start writing code. We'll see how it goes. Here's the problem. Work out the first 10 digits of the sum of the following 150-digit numbers. So what they're saying is each line here is a separate 50-digit number. So when we parse this, what we're going to have is like this here, like each line that we see, if we were to look at it in strides or something, each row of digits is one of our 50-digit numbers. The first one is the significant digit, right? So like that 3 there is a significant digit for this number. You'll notice there are no zeros in that column. So they're technically actually 50-digit numbers. They're not just sequences of 50 digits. They are 50-digit numbers, right? The zeros can only appear in the other 49 slots. Otherwise, it would be a 49-digit number. So what it wants us to do is to say, suppose we were to take the sum of all of these. Then that would give us some number. We don't know what number that would be. It'd be big, but it'd be just some number. And if we can find the highest 10 digits, the 10 digits that represent the what's the word I'm looking for? The most significant 10 digits from that sum, then we're done. That's our answer. Now, a couple things. So 50 digits is bigger than what we can store in a 64-bit number. In fact, I bet, yeah, it's even bigger than what we could store in a 128-bit number. So we can't even put one of these into an integer of like the sort of size that our CPU can do the math for us. So instead what we're going to have to do is we're going to have to do the math ourselves. Like we're going to have to write the code that handles bigger numbers than what the CPU can handle using smaller numbers, right? Like the CPU can handle a number of up to 32 bits, 64 bits, something like that, right? If we say 64 bits is what the computer can handle, how can we use that to do one of these? So let me first outline like basically how we could think of it, and then maybe like think about some ways we could simplify and see what we come up with. Problem number, what is this? Problem number 13. Problem number 13. Okay. So first of all, what is it? Let's just talk about adding two numbers, because if we can add two numbers, then we can make a number system and say, like, here's a number, what's the sum of these two? And then we can say, okay, then what's the sum of that and this, and so on and so on. And then we might also instead say, like, no, I want to be able to do an n-way sum so that I can handle all the small digits first or something. And if we do that, fine, but let's not think ahead of ourselves. Let's think about how do you add two numbers Now, that question might be kind of like a hard one to answer if you look at it, because there's the first thing that comes to mind is it sort of seems like obvious, like something, it's almost undefinable in a way. It's like you just do addition. Addition is just addition, right? So how do we break this apart? And the other thing is, like, doesn't the computer already add numbers? If the computer can't do it, then how can we make it do it? The answer is, what we're really asking how do you add two very big numbers using only small numbers? Okay, and the answer to that lies in like how you learn to do addition in like early days of arithmetic training, right? So like if I was asked to add 197 to 301, let's give it 315. How would I do this? Well, I'd write them out like this in a grid, And I'd say, first of all, I need to add 7 and 5, right? So here are our big numbers. Big numbers. And then 7 and 5. These are small numbers, right? And so then what we can do is we can go, okay, 7 plus 5, we know that. That's 12. We can do that just off the top of our head. So then what we write down is we take all of this and we transform it into this. Of course, normally you don't separate it out, but I kind of want to show how, like, it's sort of like you're creating a new state. 3, 1, 5. Boom, we put the 2 from the 12 and we put the 1. So that went right there, that went right there. So I can add two small numbers, two one-digit numbers. I get a two-digit number, and then I split that up into one-digit numbers and I move them around. So you can see how I'm using small numbers and putting them together to make big numbers, right? So we can keep going. What's the next one? Well, 1 plus 9 plus 1. 1 plus 9 plus 1 equals 11. So the same thing happens, and like, you know, I could demonstrate this again. I'll kind of like start to taper off here. Okay, what's 1 plus 1 plus 3? 1 plus 1 plus 3 equals 5. So that goes there. And so now I found out, well, 512, the sum of these guys was 512. And I found that out without actually having memorized my 3-digit addition table, right? I just used an algorithm that relied on my ability to do mental math for small numbers and applied that algorithm to some data, which was a combination of small numbers that form bigger numbers, and I got addition for bigger numbers. In other words, what we're saying is following some basic rules and the ability to do addition in small numbers gives you the ability to do addition in big numbers. So what we want to do is capture that algorithm and apply it here to these things. But I don't want to do it in decimal, right? So if I were to say, like, okay, here we go. Let's make a thing that's like turns this into an array, and 0 is the smallest part in the array, and 8 is the biggest part. Now, what's 0 plus 8? Oh, 0 plus 8 is 8. So no carry, 8 is the result. 3 plus 5 is 8, 2 plus 5 is 4. Here's a carry. 4 plus 6 is carry, so we get 1 into the carry and a 0 comes out there. And then we get 7, 2 plus 1. Oh, that's going to carry again, so 1, 0, 5, 8. Now there's a carry, right? So that's how we could do it. But you can see that this would be 50 bytes for one number. Now, I said you can't store that into 128 bits. But that doesn't mean that we have to store it in 50 bytes, right? 50 bytes, of course, would be 400 bits, and that's more than what we need. Okay, so let's think about a 50-digit number real quick. If I take 10 to the 50, that's like one bigger than the biggest 50-digit number, and I ask, what is that log 2? Right? So I'm going to take the log base 2 of that number real quick on my calculator. Okay, so I get 166. So ballpark, we need about 167 bits at least. So I think what we want to do is try to chunk this up into 64-bit chunks. And the number of 64-bit chunks we'll want is, let's see, 128 plus 64 gets you to 100. Yeah, so we'll need three. We'll need three 164-bit chunks to represent these. Okay? So first thing we're going to have to do is figure out how to decompose this into three 64-bit chunks. And then what we're going to have to do is figure out how to add two things that are 64-bit numbers into another thing that, or add two things that are like 3 by 64-bit numbers, right? So we're going to try to invent 3 by 64-bit numbers. We have 64-bit numbers. We want to invent 3 by 64-bit numbers, and we want to equip those with addition, and we want to be able to convert from a decimal representation of a number to our 3 by 64-bit number. And then we also want to be able to convert back. We want to be able to convert our 3 by 64-bit number to decimal so we can answer the question, right? So let's write those down. So here are some notes. Our numbers are in the range of 10 to the 50. Log base 2 of 10 to the 50 is approximately equal to 167. I'll say. It's actually approximately equal to 166, but I want to round up. You know, I could put it that way. I could say that number rounded up equals 167. Okay? So that's the minimum number of bits you could use to represent the numbers we have just on that screen there. But I want a little wiggle room. I want to use some 64-bit. I want to use 64-bit integers so I don't have to, like, you know, if we do a bunch of 32-bit integers to save on size, for instance, we would have to use way more of them. So it would take more math ops to actually get the process done. So I want to use 64 bits just because that's what that gives us the most number of bits, like the best ratio of how many bits we can actually use with minimum, like it maximizes how many bits we cover while minimizing how many math hops we have to do to work with it, right? So 64 bits is the target. And then it turns out that 3 times 64 equals, I think, what is it, 196? 192. So the theory is that 3 64-bit integers should be sufficient to represent our numbers. Right? And this gives us plenty of extra space. So you can see this is like 30 extra bits. 30 extra bits gives you a few billion, like a multiplier of a few billion above. Maybe not quite a few billion, but close to a billion because we didn't actually get fully 30. It's 167 and 192, so it's a little less than 30, but you get over a million multiplier. And we do have to watch out for the fact that we're going to be adding 100 of these together, which means there's kind of like you have to treat this as another 100 times multiplier. I said our range was 10 to the 50. Maybe I should have said 10 to the 52. But I still think we would have ended up at 192, right? Because that's just 100x, and this here is like a million x. So when our number of bits goes up by that much, that is. Okay. That's just numbers. Okay. So we should be able to represent our numbers using 3 64-bit integers. So here's our new problem. So plan. Invent 3 by 64 bit integer type. Equip. Let's call it 3x64u. So it's going to be an unsigned integer type. And that's 3x because we're using 3 chunks of 64 bits. Okay, call it that. And then we want to do the following. Equip it with decimal, let's see, decimal to 3x64u. So we want to equip it with that function to convert decimals to our new type. We want to equip it with, so this will be like from dec. We want to equip it with toDec. So that would give us the ability to go from a 3 by 64u to a decimal representation. And we want to equip it with the ability to go sum, right? We want this sum function, which is the ability to take two of these, 3x64u by 3x64u to another 3x64u, right? That's the things we need to be building. And finally, we can compose into a final solution. So that's the plan. So all we need to do now is focus our attention on these three problems, okay? So let's first figure out the sum one, because that's the most interesting and fun. And if we have that one figured out, that'll motivate how the rest of the system will work. And since this is the one that's going to do all the sort of compute, and this is just for display and parsing, this is one that'll how do I want to put it? Whatever choices we fix here, we can adjust these more easily, but trying to design it based on the constraints of these problems might make this harder. And so we want to take the thing that's likely to be more challenging, more interesting, etc., and try to understand it first, and that will sort of fix certain things in place that might have been less clear if we'd started from the easier end of the problem. Okay, so let's look into the sum part. I'm going to put a little divider here. Here's our sum function. So we're going to have two of these U64 things, 3 by U64s. So I'm going to say we have 3 by U64, we have an A by that name, and we have a B by that name. Or by that, we have a B of that type. Oh, did I say 3 by 64U before? Yeah, let's change that name. 3 by U64. That way it matches the... Oh, but identifiers can't begin with numbers. So let's call this a U64 by 3. How about that? Let's fix these up. U64 by 3, U64 by 3, U64 by 3 times a U64 by 3 into a U64 by 3. Now, we're going to have an A and a B. Suppose I've got two of these things, so I'm going to call them A and B, U64 by 3, U64 by 3. Now I want to think about it the same way we think about doing addition the long way. So we have three parts. I'll call it A2, A1, A0. So our least significant bits go in this part. We're going to little endian, right? Same as the byte order on our architecture and everything else that we do when we think about computers, because big endian is mostly not around anymore, as far as I know. So we lay it out kind of like this, right? Then what we do is we start adding things up. So let's just add these and see what we get. So we get, first of all, we do A0 plus B0 here. But we drop out everything that won't fit into the 64. So this is like the low part, right? That's the low 64 bits. And then we put up here A0 plus B0, the high bits, right? Then right here, we put in A1 plus B1 plus, I'm going to call this carry 0 plus carry 0, right? And we put the low part there, and then we put A1 plus B1 plus C0 high part, that's going to be carry 1. And then here, we put in another part, that's going to be A2 plus B2 plus carry 1. We put the low part there. And then finally, the high part of that comes over here. So we get like one more of these, and that's A2 plus B2 plus carry 1, the high part. Right? But then, we can't actually fit that in, so what will happen is this part is getting thrown away. This is the overflow. And this becomes our R2, R1, and R0, where R is the result of the sum, right? So we get 3 new slots that come out. So that's how the computation works. We have to do this algorithm computationally. That doesn't seem so bad, right? Yeah. So the only thing we have to figure out how we would do is how do we get the high part of a sum? That's the thing we need an answer to. If we can do that on 64-bit values, then we're good to go. So let's go digging over here. Where did my, okay, it's this one. Add. I want to see if just the add data structure, or add instruction, can help us. Do we have carry in the signed or unsigned result? Two memory operands cannot be used in one instruction. It doesn't look like this will preserve the overflow, right? Now, however, I think it might, because I think if you think about it, when you add 2 numbers together in binary, the only carry you can have is of size 1. If it's just 2 numbers, right? So let's think about this for a minute. If I'm using 1-bit numbers, right, and I add 1 plus 1, well then I get 0 and I get a carry of 1. If I add 1, 1, and 1, 1, then I get 1, 1 is going to be 1, 0. 1, 1, 1 is going to be 1, 1. And so I have here carry of 1. Two times, right? But there's nothing I can do if I'm just adding 2 of these things. No matter what I do, let me make these a little more similar. Boom, 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 boom. 1, 0, 1, 1, 1, 1, 1, 1. See, it just, you always get a carry of 1. So however many ones you have, all you're talking about is 1 carry bit. Right? Okay, so if that's true, then these things over here get simpler, because when we do this, this thing here can either be a 1 or a 0. This thing here can either be a 1 or a 0, and we have everything we need to know if they are a 1 or a 0 right here in the carry flag. That carry flag is basically the high value of the register. This is a lot simpler than like the multiplication case where you need 2 whole registers to find out how big the overflow was. We can just find out by checking the carry flag. So if I can find an easy way to read the carry flag or to jump on it or something, that should be all I need. It evaluates the result for both signed and unsigned integer operands. Indicate a carry overflow in the signed or unsigned result. Circulate the signed flag. Signed result. Yeah. Okay. So let me go back to JCC. That would give me one way to do it. If I can find something that only jumps on the carry flag. Jump short if carry. Yeah, so I could just do JC. That'll jump. Jump if carry. So yeah, I can also jump if carry. Jump if carry. Yeah, you jump if there was a carry. Is there any way to do jump if not carry? I mean, I see that we actually do have it here. It's just not helpfully named not carry, right? There's not a version where the name jump near if not carry. NC. Okay, cool. So not carry. So if we can do that, we can use C and NC for carry and not carry conditions. Then we can do an addition, find out if there was a carry, and then if there was, so the other trick here is once you have a carry of 1, you have to watch out because that carry of 1, yeah, so the harder part is when you have 3 numbers like this and you want to find out if they carry or not. And I guess the way you would do it is first you add these together, and if they carry, then the whole thing carries, and if not, then you add this in, and if that carries, it's also a carry, right? Perhaps another way you could do it is you could start by, let's play with the algorithm for a minute here. So we could start by just doing, like, let's just see what happens if we ignore the carry part, right? So we just start with R0 equals A0 plus B0. And then let's also say, like, we grab the carry bit at the same time, but we don't do anything else, right? We'll store whether or not there was a carry, but we won't actually add that in anywhere. Carry 1 is A1 plus B1. Carry 2, results 2 equals A2 plus B2. And then what we want to do is we want to update R1C1. So C1 here is like, it might already contain a carry. I don't want to do C1 R1 equals R1 plus C0. So I could do something like this, except I could be losing the correct value of the carry bit. So I need, like, I'm going to change up the notation here. C sub 0, R sub 0 equals A sub 0 plus B sub 0. C sub 1 dot R sub 1 equals R sub 1 dot equals A1 plus B1. C sub 1 x equals comma R1 equals R1 dot plus C0. C1 equals C1 dot or C1x. Is this correct? Hopefully what I'm writing here is sort of making sense. So the idea is we do an add, we put the main result in R0 and the carry into C0. Now we know that one's correct. Now the problem is we want to add 3 things together in the next case. But if we add in 3 things all at once, we don't have an operation that actually lets us do that. So instead we do A1 plus B1, but that's losing the carry. And A1 plus B1 might carry. Yeah, this would definitely calculate the right thing. I don't know if it's the most efficient way to calculate it, but it would calculate the right thing. You'd have to pay attention to 2 separate carries on 2 separate additions, and this one would just be adding a 1 or a 0. But I don't know if there's any obvious way to get it right in every case without doing it this way. What happens if A1 and B1 are the maximum they can possibly be? Well, then obviously they have a carry. When you add 1, there would be a 0 there. So you can't get a carry of 2 even if you added another carry here. The only way that this produces a carry that you didn't already see here is if A1 plus B1 is like 1 less than the maximum value of a 64-bit. Like, all of this is exactly this max value, right? So if that is 1, 1, 1, 1, 1, 1, or whatever, and we then look at C0 and that has a carry, then we get a carry here but not here. So what I wonder is, could we, using that kind of logic, I'm going to use like different notation because it's a little bit hard to read. Suppose I did C1 R1, C2 R2. We could just knock out all the adds right away. And then we have to do C1 hat R1 equals R1 bar plus C0. C1 equals C1 hat or C1 bar. C2 hat are, we don't care about C2 technically. So then we just do R2 equals R2 bar plus C1. That seems good. I mean, that seems easy enough, right? Like, we have to do 3 separate adds where we look at the carry. We get 1, 2, 3, 4 total adds. And we have 5 total adds. 1, 2, 3, 4, 5. 1 for the first pair of digits, 2 for every following pair of digits. So 5 adds, 1 or, because there's only one spot where the carry is a sum of, there's only one spot where we have to accumulate 3 values into a carry. We don't have to do it here because we never have a carry for C0. Like, we never have a carry over here. So that doesn't have to do it. And this doesn't have to do it because we don't calculate the carry on R2. So 1, 2, 3, 4, 5, 6. This seems like a good situation, right? So I think that's how we'll do it. So now, what's the other stuff we have to do in this problem? We need to figure out how on earth we're going to do decimal conversions. So that could actually be pretty tricky. Let's think about that for a little bit. How will we do decimal to U64 by 3? So the way I would normally do decimal to like a U64 is you read in an integer from the stream, and then you multiply by 10, and then you read in another integer, add that in, multiply by 10, read in another integer, add that in, until you're done accumulating all of the integers, one digit at a time. So you pull out digits in decimal, and you pack them in. But that requires multiplication by 10. Furthermore, if I were going to do U64 by 3 to decimal, then it goes the other way around. You have to be able to do division and modulo, so you have to get like the remainder. My normal, come on, bring me back the, there we go. My normal scheme requires division by 10. So if I do it the way I normally do it, I would have to equip these things with multiplication and division as well. At least multiplication and division by a small number. Now that's different, right? I don't have to do full U64 x3 divided by 10. Like, I don't have to do U64 by 3 divided by U64 divided by 3. I just have to support U64 by 3 divided by 3, right? I'd have to be able to support this version, is what I'm trying to say. the version that just takes in a U64 by 3 and a U64, right? It would be harder if I had to do 2 of these, because then I have to do division on multiple parts for both of them. But maybe we can do it more easily if there's just one of them is big and one of them is small. Same thing with multiplication. So we could do long multiplication and long division. That's something we could do. But I think I'll leave it there. So we've kind of got an idea of what we need to do, but in order to do the rest of it, we want to work out how to do long multiplication and long division. We'll work that out next time, and then we'll write the code for all these ideas. So that'll leave us with kind of a pretty interesting problem to solve, and then we'll have, we'll knocked out these 3 data processing problems where we had to do the parser, and we'll be on to new problems after that. And we got 2 done this time, which is pretty good. That's the good pace. So we got some ground covered for the next one. I'll start prepping my mind so that next time when I'm fresh we can do these guys. And yeah. The only other thing to consider is maybe we could do this problem. I was being ambitious in saying, what if we did it all in like 192 bits? The other thing we could do is say like, okay, we're going to do this in a base that's not base 2. So the way we could look at it is like, okay, 1, 2, so there's 3, 6, let's say 3, 6, 9. So like maybe somewhere like right here, right, where you got 10 digits. Or better yet, we'll say 9 digits. No, hold on, let me think. So 2 to the 64, how many digits can you do with 2 to the 64? 19, 18. So you could do 18 digits. That's what I should say. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Right? So we could break this up into 18-digit parts and put each of those into 64 bits. It wouldn't quite be what we were doing before, because instead of saying, hey, we'll just use 64-bit numbers, what we're actually saying is we're using each of the numbers is like modulo some power of 10. That way, when we are unpacking these, we can just unpack them using like the fact that like, okay, here is a section of digits. Here is a section of digits, right? Like you could chop up the digits separately using just the characters themselves. And that would avoid long multiplication and long division. But then it would complicate the addition part. So that'll be the alternative. Let me note that idea here too. All right, let's think about that next time. All right. I think that's where I will wrap it up for tonight. So thanks for coming to hang out, and I'll see you guys next time.